双语音标领航，注音阅读启蒙，叶兴阳有声读物。
A History of Science, Volume 4, by Henry Smith Williams, M.D., LL.D., assisted by Edward H. Williams, M.D., in 5 volumes. Volume 4, Modern Development of the Chemical and Biological Sciences. A History of Science. Book 4. Modern Development of the Chemical and Biological Sciences. A.S. regards chronology. The epoch covered in the present volume is identical with that viewed in the preceding one. But now, as regards subject matter, we pass on to those diverse phases of the physical world which are the field of the chemist, and to those yet more intricate processes which have to do with living organisms. So radical are the changes here that we seem to be entering new worlds, and yet, here as before, there are intimations of the new discoveries away back in the Greek days. The solution of the problem of respiration will remind us that Anaxagoras half guessed the secret, and in those diversified studies which tell us of the Daltonian atom in its wonderful transmutations, we shall be reminded again of the Clazomenian philosopher and his successor, Democritus. Yet we should press the analogy much too far were we to intimate that the Greek of the elder day, or any thinker of a more recent period, had penetrated, even in the vaguest way, all of the mysteries that the 19th century has revealed in the fields of chemistry and biology. At the very most, the insight of those great Greeks and of the wonderful 17th century philosophers who so often seemed on the verge of our later discoveries did no more than vaguely anticipate their successors of this later century. To gain an accurate, really specific knowledge of the properties of elementary bodies was reserved for the chemists of a recent epoch. The vague Greek questionings as to organic evolution were worldwide from the precise inductions of a Darwin. If the medieval Arabian endeavored to dull the knife of the surgeon with the use of drugs, his results hardly merit to be termed even an anticipation of modern anesthesia. And when we speak of preventive medicine of bacteriology in all its phases, we have to do with a marvelous field of which no previous generation of men had even the slightest inkling. All in all, then, those that lie before us are perhaps the most wonderful and the most fascinating of all the fields of science. As the chapters of the preceding book carried us out into a macrocosm of inconceivable magnitude, our present studies are to reveal a microcosm of equally inconceivable smallness. As the studies of the physicist attempted to reveal the very nature of matter and of energy, we have now to seek the solution of the yet more inscrutable problems of life and of mind. The phlogiston theory in chemistry. The development of the science of chemistry from the science of alchemy is a striking example of the complete revolution in the attitude of observers in the field of science. As has been pointed out in a preceding chapter, the alchemist, having a preconceived idea of how things should be, made all his experiments to prove his preconceived theory, while the chemist reverses this attitude of mind and bases his conceptions on the results of his laboratory experiments. In short, chemistry is what alchemy never could be, an inductive science. But this transition from one point of view to an exactly opposite one was necessarily a very slow process. Ideas that have held undisputed sway over the minds of succeeding generations for hundreds of years cannot be overthrown in a moment, unless the agent of such an overthrow be so obvious that it cannot be challenged. The rudimentary chemistry that overthrew alchemy had nothing so obvious and palpable. The great first step was the substitution of the one principle, phlogiston, for the 3 principles, salt, sulfur, and mercury. We have seen how the experiment of burning or calcining such a metal as lead destroyed the lead as such, leaving an entirely different substance in its place, and how the original metal could be restored by the addition of wheat to the calcined product. To the alchemist, this was mortification and revivification of the metal. For, as pointed out by Paracelsus, anything that could be killed by man could also be revivified by him, although this was not possible to the things killed by God. The burning of such substances as wood, wax, oil, etc., was also looked upon as the same killing process, and the fact that the alchemist was unable to revivify them was regarded as simply the lack of skill on his part, and in no wise affecting the theory itself. But the iconoclastic spirit, if not the acceptance of all the teachings of the great Paracelsus, had been gradually taking root among the better class of alchemists, and about the middle of the 17th century Robert Boyle, 1626 to 1691, called attention to the possibility of making a wrong deduction from the phenomenon of the calcination of the metals, because of a very important factor, the action of the air, which was generally overlooked. And he urged his colleagues of the laboratories to give greater heed to certain other phenomena that might pass unnoticed in the ordinary calcinating process. In his work, The Skeptical Chemist, he showed the reasons for doubting the threefold constitution of matter, and in his general history of the air advanced some novel and carefully studied theories as to the composition of the atmosphere. This was an important step, and although Boyle is not directly responsible for the phlogiston theory, it is probable that his experiments on the atmosphere influenced considerably the real founders, Becher and Stahl. Boyle gave very definitely his idea of how he thought air might be composed. I conjecture that the atmospherical air consists of 3 different kinds of corpuscles. He says, the first, those numberless particles, which, in the form of vapors or dry exhalations, ascend from the earth, water, minerals, vegetables, animals, etc. In a word, whatever substances are elevated by the celestial or subterranean heat, and thence diffused into the atmosphere. The second may be yet more subtle, and consist of those exceedingly minute atoms, the magnetical effluvia of the earth, with other innumerable particles sent out from the bodies of the celestial luminaries, and causing, by their influence, the idea of light in us. The third sort is its characteristic and essential property, permanently elastic parts. Various hypotheses may be framed relating to the structure of these later particles of the air. They might be resembled to the springs of watches, coiled up and endeavoring to restore themselves to wool, which, being compressed, has an elastic force, to slender wires of different substances, consistencies, lengths, and thickness, in greater curls or less, near to or remote from each other, etc., yet all continuing springy, expansible, and compressible. Lastly, they may also be compared to the thin shavings of different kinds of wood, various in their lengths, breadth, and thickness. And this, perhaps, will seem the most eligible hypothesis, because it, in some measure, illustrates the production of the elastic particles we are considering. For no art or curious instruments are required to make these shavings whose curls are in no wise uniform, but seemingly casual, and, what is more remarkable, bodies that before seemed unelastic, as beams and blocks, will afford them. 1. Although this explanation of the composition of the air is most crude, it had the effect of directing attention to the fact that the atmosphere is not mere nothingness, but a something with a definite composition, and this served as a good foundation for future investigations. To be sure, Boyle was neither the first nor the only chemist who had suspected that the air was a mixture of gases, and not a simple one, and that only certain of these gases take part in the process of calcination. Jean Rey, a French physician, and John Mayo, an Englishman, had preformed experiments which showed conclusively that the air was not a simple substance, but Boyle's work was better known, and in its effect probably more important. But with all Boyle's explanations of the composition of air, he still believed that there was an inexplicable something, a vital substance, which he was unable to fathom, and which later became the basis of Stahl's phlogiston theory. Commenting on this mysterious substance, Boyle says, "The difficulty we find in keeping flame and fire alive, though but for a little time, without air, renders it suspicious that there be dispersed through the rest of the atmosphere some odd substance, either of a solar, astral, or other foreign nature, on account of which the air is so necessary to the substance of flame." It was this idea that attracted the attention of George Ernst Stahl, 1660 to 1734, a professor of medicine in the University of Halle, who later founded his new theory upon it. Stahl's theory was a development of an earlier chemist, Johann Joachim Becher, 1635 to 1682, in whose footsteps he followed and whose experiments he carried further. In many experiments, Stahl had been struck with the fact that certain substances, while differing widely from one another in many respects, were alike in combustibility. From this he argued that all combustible substances must contain a common principle, and this principle he named phlogiston. This phlogiston he believed to be intimately associated in combination with other substances in nature, and in that condition not perceivable by the senses. But it was supposed to escape as a substance burned, and become apparent to the senses as fire or flame. In other words, phlogiston was something imprisoned in a combustible structure, itself forming part of the structure, and only liberated when the structure was destroyed. Fire, or flame, was free phlogiston, while the imprisoned phlogiston was called combined phlogiston, or combined fire. The peculiar quality of this strange substance was that it disliked freedom and was always striving to conceal itself in some combustible substance. Boyle's tentative suggestion that heat was simply motion was apparently not accepted by Stahl, or perhaps it was unknown to him. According to the phlogistic theory, the part remaining after a substance was burned was simply the original substance deprived of phlogiston. To restore the original combustible substance, it was necessary to heat the residue of the combustion with something that burned easily, so that the freed phlogiston might again combine with the ashes. This was explained by the supposition that the more combustible a substance was, the more phlogiston it contained, and since free phlogiston sought always to combine with some suitable substance, it was only necessary to mix the phlogisticating agents, such as charcoal, phosphorus, oils, fats, etc., with the ashes of the original substance, and heat the mixture, the phlogiston thus freed uniting at once with the ashes. This theory fitted very nicely as applied to the calcined lead revivified by the grains of wheat, although with some other products of calcination it did not seem to apply at all. It will be seen from this that the phlogistic theory was a step towards chemistry and away from alchemy. It led away from the idea of a spirit in metals that could not be seen, felt, or appreciated by any of the senses, and substituted for it a principle which, although a falsely conceived one, was still much more tangible than the spirit, since it could be seen and felt as free phlogiston and weighed and measured as combined phlogiston. The definiteness of the statement that a metal, for example, was composed of phlogiston and an element was much less enigmatic, even if wrong, than the statement of the alchemist that metals are produced by the spiritual action of the three principles: salt, mercury, sulfur, particularly when it is explained that salt, mercury, and sulfur were really not what their names implied, and that there was no universally accepted belief as to what they really were. The metals, which are now regarded as elementary bodies, were considered compounds by the phlogistians, and they believed that the calcining of a metal was a process of simplification. They noted, however, that the remains of calcination weighed more than the original product, and the natural inference from this would be that the metal must have taken in some substance rather than have given off anything. But the phlogistians had not learned the all-important significance of weights, and their explanation of variation in weight was either that such gain or loss was an unimportant accident at best, or that phlogiston, being light, tended to lighten any substance containing it, so that driving it out of the metal by calcination naturally left the residue heavier. At first, the phlogiston theory seemed to explain in an indisputable way all the known chemical phenomena. Gradually, however, as experiments multiplied, it became evident that the plain theory as stated by Stahl and his followers failed to explain satisfactorily certain laboratory reactions. To meet these new conditions, certain modifications were introduced from time to time, giving the theory a flexibility that would allow it to cover all cases. But as the number of inexplicable experiments continued to increase, and new modifications to the theory became necessary, it was found that some of these modifications were directly contradictory to others, and thus the simple theory became too cumbersome from the number of its modifications. Its supporters disagreed among themselves, first as to the explanation of certain phenomena that did not seem to accord with the phlogistic theory, and, a little later, as to the theory itself. But as yet there was no satisfactory substitute for this theory, which, even if unsatisfactory, seemed better than anything that had gone before or could be suggested. But the good effects of the era of experimental research, to which the theory of Stahl had given such an impetus, were showing in the attitude of the experimenters. The works of some of the older writers, such as Boyle and Hooke, were again sought out in their dusty corners and consulted, and their surmises as to the possible mixture of various gases in the air were more carefully considered. Still, the phlogiston theory was firmly grounded in the minds of the philosophers, who can hardly be censured for adhering to it, at least until some satisfactory substitute was offered. The foundation for such a theory was finally laid, as we shall see presently, by the work of Black, Priestley, Cavendish, and Lavoisier in the 18th century. But the phlogiston theory cannot be said to have finally succumbed until the opening years of the 19th century.
2.
The beginnings of modern chemistry. The pneumatic chemists. Modern chemistry may be said to have its beginning with the work of Stephen Hales, 1677 to 1761, who early in the 18th century began his important study of the elasticity of air. Departing from the point of view of most of the scientists of the time, he considered air to be a fine elastic fluid, with particles of very different nature floating in it, and he showed that these particles could be separated. He pointed out, also, that various gases, or airs, as he called them, were contained in many solid substances. The importance of his work, however, lies in the fact that his general studies were along lines leading away from the accepted doctrines of the time, and that they gave the impetus to the investigation of the properties of gases by such chemists as Black, Priestley, Cavendish, and Lavoisier, whose specific discoveries are the foundation stones of modern chemistry. Joseph Black. The careful studies of Hales were continued by his younger confrere, Dr. Joseph Black, 1728 to 1799, whose experiments in the weights of gases and other chemicals were first steps in quantitative chemistry. But even more important than his discoveries of chemical properties in general was his discovery of the properties of carbonic acid gas. Black had been educated for the medical profession in the University of Glasgow, being a friend and pupil of the famous Dr. William Cullen. But his liking was for the chemical laboratory rather than for the practice of medicine. Within 3 years after completing his medical course, and when only 23 years of age, he made the discovery of the properties of carbonic acid, which he called by the name of fixed air. After discovering this gas, Black made a long series of experiments, by which he was able to show how widely it was distributed throughout nature. Thus, in 1757, he discovered that the bubbles given off in the process of brewing, where there was vegetable fermentation, were composed of it. To prove this, he collected the contents of these bubbles in a bottle containing lime water. When this bottle was shaken violently, so that the lime water and the carbonic acid became thoroughly mixed, an insoluble white powder was precipitated from the solution, the carbonic acid having combined chemically with the lime to form the insoluble calcium carbonate, or chalk. This experiment suggested another. Fixing a piece of burning charcoal in the end of a bellows, he arranged a tube so that the gas coming from the charcoal would pass through the lime water, and, as in the case of the bubbles from the brewer's vat, he found that the white precipitate was thrown down. In short, that carbonic acid was given off in combustion. Shortly after, Black discovered that by blowing through a glass tube inserted into lime water, chalk was precipitated, thus proving that carbonic acid was being constantly thrown off in respiration. The effect of Black's discoveries was revolutionary, and the attitude of mind of the chemists towards gases, or airs, was changed from that time forward. Most of the chemists, however, attempted to harmonize the new facts with the older theories to explain all the phenomena on the basis of the phlogiston theory, which was still dominant. But while many of Black's discoveries could not be made to harmonize with that theory, they did not directly overthrow it. It required the additional discoveries of some of Black's fellow scientists to complete its downfall, as we shall see. Henry Cavendish. This work of Black's was followed by the equally important work of his former pupil, Henry Cavendish, 1731 to 1810, whose discovery of the composition of many substances, notably of nitric acid and of water, was of great importance, adding another link to the important chain of evidence against the phlogiston theory. Cavendish is one of the most eccentric figures in the history of science, being widely known in his own time for his immense wealth and brilliant intellect, and also for his peculiarities and his morbid sensibility, which made him dread society, and probably did much in determining his career. Fortunately for him, and incidentally for the cause of science, he was able to pursue laboratory investigations without being obliged to mingle with his dreaded fellow mortals, his every want being provided for by the immense fortune inherited from his father and an uncle. When a young man, as a pupil of Dr. Black, he had become imbued with the enthusiasm of his teacher, continuing Black's investigations as to the properties of carbonic acid gas when free and in combination. One of his first investigations was reported in 1766, when he communicated to the Royal Society his experiments for ascertaining the properties of carbonic acid and hydrogen gas, in which he first showed the possibility of weighing permanently elastic fluids, although Torricelli had before this shown the relative weights of a column of air and a column of mercury. Other important experiments were continued by Cavendish, and in 1784 he announced his discovery of the composition of water, thus robbing it of its time-honored position as an element. But his claim to priority in this discovery was at once disputed by his fellow countryman James Watt and by the Frenchman Lavoisier. Lavoisier's claim was soon disallowed even by his own countrymen. But for many years a bitter controversy was carried on by the partisans of Watt and Cavendish. The two principals, however, seem never to have entered into this controversy with anything like the same ardor as some of their successors, as they remained on the best of terms. 1. It is certain, at any rate, that Cavendish announced his discovery officially before Watt claimed that the announcement had been previously made by him, and, whether right or wrong, the honor of scientific discoveries seems to be accorded naturally to the man who first publishes a demonstration of his discovery. Englishmen very generally admit the justness of Cavendish's claim, although the French scientist Arago, after reviewing the evidence carefully in 1833, decided in favor of Watt. It appears that something like a year before Cavendish made known his complete demonstration of the composition of water, Watt communicated to the Royal Society a suggestion that water was composed of dephlogisticated air, oxygen, and phlogiston, hydrogen, deprived of part of its latent heat. Cavendish knew of the suggestion, but in his experiments refuted the idea that the hydrogen lost any of its latent heat. Furthermore, Watt merely suggested the possible composition without proving it, although his idea was practically correct, if we can rightly interpret the vagaries of the nomenclature then in use. But had Watt taken the steps to demonstrate his theory, the great water controversy would have been avoided. Cavendish's report of his discovery to the Royal Society covers something like 40 pages of printed matter. In this he shows how, by passing an electric spark through a closed jar containing a mixture of hydrogen gas and oxygen, water is invariably formed, apparently by the union of the two gases. The experiment was first tried with hydrogen and common air, the oxygen of the air uniting with the hydrogen to form water, leaving the nitrogen of the air still to be accounted for. With pure oxygen and hydrogen, however, Cavendish found that pure water was formed, leaving slight traces of any other substance which might not be interpreted as being chemical impurities. There was only one possible explanation of this phenomenon, that hydrogen and oxygen, when combined, form water, By experiments with the globe it appeared, wrote Cavendish, that when inflammable and common air are exploded in a proper proportion, almost all the inflammable air, and near 1/5 the common air, lose their elasticity and are condensed into dew. And by this experiment it appears that this dew is plain water, and consequently that almost all the inflammable air is turned into pure water. In order to examine the nature of the matter condensed on firing a mixture of dephlogisticated and inflammable air, I took a glass globe, holding 8,800 grain measures, furnished with a brass cock and an apparatus for firing by electricity. This globe was well exhausted by an air pump, and then filled with a mixture of inflammable and dephlogisticated air by shutting the cock, fastening the bent glass tube into its mouth, and letting up the end of it into a glass jar inverted into water and containing a mixture of 19,500 grain measures of dephlogisticated air and 37,000 of inflammable air, so that, upon opening the cock, some of this mixed air rushed through the bent tube and filled the globe. The cock was then shut, and the included air fired by electricity, by means of which almost all of it lost its elasticity, was condensed into water vapors. The cock was then again opened so as to let in more of the same air to supply the place of that destroyed by the explosion, which was again fired, and the operation continued till almost the whole of the mixture was let into the globe and exploded. By this means, though the globe held not more than 1/6 part of the mixture, almost the whole of it was exploded therein without any fresh exhaustion of the globe. At first this condensed matter was acid to the taste and contained 2 grains of nitre, but Cavendish, suspecting that this was due to impurities, tried another experiment that proved conclusively that his opinions were correct. I therefore made another experiment, he says, with some more of the same air from plants in which the proportion of inflammable air was greater, so that the burnt air was almost completely phlogisticated, its standard being 1/10. The condensed liquor was then not at all acid, but seemed pure water. From these experiments he concludes that when a mixture of inflammable and dephlogisticated air is exploded, in such proportions that the burnt air is not much phlogisticated, the condensed liquor contains a little acid which is always of the nitrous kind, whatever substance the dephlogisticated air is procured from. But if the proportion be such that the burnt air is almost entirely phlogisticated, the condensed liquor is not at all acid, but seems pure water, without any addition whatever. 2. These same experiments, which were undertaken to discover the composition of water, led him to discover also the composition of nitric acid. He had observed that, in the combustion of hydrogen gas with common air, the water was slightly tinged with acid, but that this was not the case when pure oxygen gas was used. Acting upon this observation, he devised an experiment to determine the nature of this acid. He constructed an apparatus whereby an electric spark was passed through a vessel containing common air.